Hello and welcome to Factive, your home for knowledge in 5 minutes or less. My name is Sean, so sit back and relax because today we're learning about quantum entanglement. Let's get started. To understand quantum entanglement, let's first talk about quantum superposition. The most famous example of this concept is known as Schrödinger's cat. In this thought experiment, a cat is placed in a soundproof box along with a Geiger counter, a radioactive source, and a vial of poison. If the Geiger counter detects radiation, the vial shatters and the poison kills the cat. An observer outside the box would never know if or when the poison was triggered, so while the box is still closed, the cat is both alive and dead. In a less deadly scenario, take two identical boxes and put a cake in one box and a pie in the other. If you were to give those boxes to a friend, each box would contain both a cake and a pie simultaneously until they open the box to confirm. And if they open one box and it contains a pie, then they know that the other box contains a cake. Superposition is the ability of a quantum particle to exist in multiple states until it is measured. Quantum entanglement occurs when particles link and their states become dependent, regardless of distance. Subatomic particles have a property known as spin, which is a bit of a misnomer because particles don't actually spin, but they do have angular momentum. We can classify spin as up or down, two equal and opposite states. Entangled particles exist in a state of superposition, where both spin up and down until measured. If particle A is measured as upspin, then particle B has downspin. These opposite states occur whether the particles are 10 feet or 10 galaxies away. This implies faster than light communication, a reality that Einstein himself called spooky action at a distance. He was pretty unnerved by a quantum property that broke the laws of relativity. Here's where it gets even weirder. If the particles exist in both up and down spin states until we measure them, thanks to superposition, there's no telling whether the act of measurement influenced that particle's state. Our interaction may force the particle into a particular state, forcing its entangled counterpart into the opposite state. If that's the case, we may be affecting particles on the opposite side of the universe all the time and not even know it. This phenomenon creates another issue. While we can know the state of the second particle by measuring the first, we can't know whether we affected its state or conditions on the other side of the universe did. Using quantum entanglement as a method of communication becomes less viable when you can't be sure who is sending the message. While quantum entanglement may not be as helpful for communication, if you can set an entangled particle state in a predictable way, such as where spin equates to a 0 or a 1 instead of up or down, you create a unique opportunity. In computing, a 0 and a 1 would be the two states of a bit, the components of binary code that can be used to transmit numbers and letters and do complex calculations. We can get into quantum computing in another video, but the possibility that entangled particles can be a 0 and a 1 simultaneously opens up entire worlds in computing technology. Think of trying to crack a code and you can try every possible combination at once. It's scary and fascinating. Well, that, my friends, is the end of today's video. For some deeper dives into this topic, see the links in the description below. Also, leave a like and a comment about what factive topics you want me to cover next. Until next time, have a good one.